In the late summer of 1507, a wall of rock and mud came off Mount Rainier, ran more than 60 kilometers down the Puyallup Valley, and buried a standing forest under 30 meters of debris. This year, researchers read the rings of the trees it killed and pinned the year exactly. Then they went looking for the eruption that caused it. There is no ash layer, no matching earthquake, and no explanation. By the end of this, you will understand what is actually eating this mountain, and why the town built on that mudflow gets 50 minutes. Mount Rainier is not going to erupt anytime soon, and that is exactly the problem. The alert level is green. It has been green for the entire modern monitoring era. The last confirmed large eruptions happened roughly 1,100 and 2,300 years ago. By every standard people usually apply to a volcano, this one is asleep. And it is still the most dangerous volcano in the United States, because the thing that makes it dangerous has nothing to do with magma. Inside that mountain, hot, acidic, sulfur-bearing water has been circulating through solid rock for thousands of years. That water does not build pressure. It does not push toward the surface. It does something slower and far harder to monitor. It chemically dismantles the rock it touches, converting hard, load-bearing volcanic stone into soft clay. The process runs whether or not magma is moving. It runs whether or not the mountain is doing anything a seismometer would notice. And it has been running, uninterrupted, through the entire millennium of quiet that convinced everyone this mountain was safe. Roughly 90,000 people live downhill of the result. The rock that builds Mount Rainier is andesite. Fresh andesite is strong, brittle, and competent, meaning it holds weight and holds shape. It is the material that lets a stratovolcano stand 14,411 feet above the surrounding country at slope angles that would be impossible in softer stone. Hydrothermal alteration takes that material apart at the mineral level. Acidic fluid moving through cracks and pore spaces attacks the minerals in the andesite and replaces them with clay minerals and soft alteration products. The rock does not shatter. It does not visibly crumble. It simply stops being strong. It loses cohesion, it loses internal friction, and it stops resisting the forces that want to pull it downhill. There are two consequences, and the second one is worse than the first. The first consequence is that altered rock is much more likely to fail all at once rather than shedding material gradually. A healthy slope sheds rockfall continuously and relieves stress as it goes. A slope full of clay holds together until it does not, and then a very large piece of it moves at the same time. The second consequence is what the clay does after the failure. Clay is what allows a debris flow to keep flowing. A landslide made of clean, dry rock will run out of energy, dewater, and stop within a few kilometers of the mountain. A landslide loaded with clay holds its water, stays fluid, and keeps moving for tens of kilometers past the base of the volcano. The chemistry that weakens the mountain is the same chemistry that gives the resulting flow its range. That combination is what turns a cascade volcano into something that can reach a suburb. This is not a hypothesis about what might be happening inside the mountain. A survey published in the Journal of Volcanology and Geothermal Research in 2008 mapped the extent and intensity of the alteration across the edifice from rock samples and linked that distribution directly to debris flow hazard. Geologists know which parts of Mount Rainier have been chemically compromised. They know how badly, and they know it from the minerals in the rock rather than from a model. The altered material is visibly different, pale, soft, crumbling in the hand where fresh andesite would ring under a hammer. In 2001, 3 researchers, Reed, Sisson, and Bryan, published a modeling study in the journal Geology asking a specific question about Mount Rainier. Where on this mountain can a large flank collapse actually initiate? Their answer was unusually precise for a hazard assessment. A sizable collapse, anything larger than 1/10 of a cubic kilometer, requires 3 conditions in the same place. It requires a large volume of weak, hydrothermally altered rock. It requires that rock to sit high on the edifice, and it requires the slope beneath it to be steep. Any 2 of those conditions is a geology problem. All 3 together is a countdown. It is worth pausing on how low that threshold is. 1/10 of a cubic kilometer sounds substantial, and it is, but it is roughly 1/40th of the largest collapse this mountain has actually produced. The modeling is not describing a worst case. It is describing the smallest failure that still counts as sizable and asking where on the mountain even that is possible. On Mount Rainier, those 3 conditions coincide in exactly one place, the upper west slope. Nowhere else on the mountain satisfies all of them. That sector has a name. It is called the Sunset Amphitheater, a headwall region west of the modern summit above the Tahoma Glacier. Beneath it sits an appreciable thickness of water-saturated, hydrothermally altered rock, more than 500 meters of it. The United States Geological Survey states the position plainly. The greatest hazard from landslide-generated lahars is on the west side of the volcano, because the west side contains the largest amount of hydrothermally weakened rock. And this is not a modeling result waiting for confirmation. Within the last 100 years, a rock avalanche came off that headwall onto the Tahoma Glacier, and the debris it left behind contains magmatic hydrothermal alteration minerals. The weak rock is not inferred from a computer. It has already failed at small scale, close enough to the present day that the deposit is still identifiable on the glacier. To understand what happens when that failure occurs at full scale, you do not need a simulation. You need to look at the ground people are currently living on. In the late summer of a single year more than 500 years ago, a mass of material came off Mount Rainier and moved into the Puyallup River drainage. It did not stop at the base of the mountain. It traveled more than 60 kilometers down the valley. It arrived at the community now called Electron, carrying enough material to bury the valley floor under roughly 30 meters of rock, mud, and water, about 98 feet. It hit a standing forest on the way. Not brush, not saplings. Mature Douglas fir, some of them 3 meters thick at the trunk. The flow snapped them, knocked them flat, and buried them where they fell. And because the burial was fast and total, those trees did not rot. They were sealed under the deposit with their bark still attached. That event is called the Electron Mudflow. It is the largest lahar Mount Rainier has produced in the past 1,000 years. Now here is the part that should change how you look at a map of Washington state. The material that flow deposited did not get cleaned up. It is still there. It forms the surface of the valley floor around Orting, Washington, a town of roughly 8,500 people sitting at the confluence of the Puyallup and Carbon rivers. The ground under Orting is the mudflow. People built a town on the deposit because the deposit is flat, fertile, and easy to build on, which is exactly what a large debris flow leaves behind when it finally stops. And until this year, nobody could say precisely when it happened. That changed with a study published in the journal Geology in volume 54 by Brian Black, Patrick Pringle, and James Vallance. The title is direct: Forest Floor Burial in 1507 by the largest Mount Rainier lahar of the past millennium. The method is worth walking through because the precision of the answer is what makes the conclusion so uncomfortable. They started with radiocarbon. 7 radiocarbon ages were taken from the buried bark-bearing trees and wiggle-matched against the calibration curve. That narrowed the event to somewhere between 1477 and 1522, with 99.7% certainty. A 45-year window is good, but it is not an answer. So they went to the tree rings. Every tree killed by that flow recorded the local climate in its growth rings right up to the moment it died. And those patterns of wide and narrow rings are effectively a fingerprint of a specific run of years. The team sampled 21 trees killed by the lahar and measured 86 separate time series from them for statistical verification. Then they cross-dated that combined pattern against living and archived chronologies from elsewhere in the region. The electron pattern matched best against low-elevation chronologies, and in particular against a Douglas fir chronology from Vancouver Island in British Columbia. The match pinned the death year exactly, 1507. They got one more thing out of the wood. In the final ring of those trees, the late wood, the darker, denser growth a conifer lays down at the end of the growing season, was only beginning to form. The trees died in the late summer, not just the year, the season. That detail is not trivia. It is the piece of evidence that starts eliminating suspects. The reason this technique works at all is that trees in the same climate region grow in step with one another. A cold year is narrow in every tree that experienced it, a favorable year is wide, and across a century that produces a sequence specific enough to place a piece of dead wood in absolute time. The Vancouver Island match matters, because it means the buried electron trees were responding to the same regional weather as trees hundreds of kilometers north, which is what allows the year to be stated without a margin of error attached to it. With a firm year in hand, the obvious next step was to find the eruption. That is how this is supposed to work. A large lahar comes off a volcano because the volcano did something. Magma rises, the summit fails. A frito-magmatic blast tears into the ice cap, and the resulting slurry runs down a river valley. If Mount Rainier erupted in 1507, it would have left to Fra a layer of ash somewhere in the regional record, in a lakebed or a bog or a soil profile, sitting at the right position in the sequence. The researchers looked. Here is the finding, stated as plainly as the research summary states it. No ash layer has been found that would correspond to a 1507 eruption at Mount Rainier. They also checked the other obvious culprit. The Cascadia subduction zone, offshore of Washington, last produced a great earthquake in the year 1700, and that event is known precisely enough to test against. 1700 is not 1507. The dates do not match. Cascadia did not do this. So the largest debris flow this mountain has produced in 1,000 years, a flow that moved 60 kilometers, buried a forest, and laid down the ground a town now sits on, has no identified eruptive trigger and no identified earthquake trigger. The cause is unknown. Sit with what that means for a moment, because it is the whole argument. Mount Rainier is monitored extensively and competently for the signs that precede an eruption: seismic swarms, ground deformation, changes in gas emissions. That entire architecture assumes the catastrophe announces itself. And the most recent catastrophe this mountain actually produced did not leave the announcement behind. The researchers did not leave it at unknown. They named 3 candidate triggers, and each one is worth understanding because each implies something different about how much warning anyone would get next time. The first candidate is an eruption too small to preserve. It is possible Mount Rainier did erupt in 1507, but produced so little tephra that no layer survived in the record. This is the most reassuring option because it keeps the eruption monitoring model intact. It is also the weakest because it requires assuming evidence that has never been found. The second candidate is a hydrothermal explosion. Inside altered rock, a pocket of pressurized hot fluid can fail explosively with no new magma involved at all. Nothing rises from below. Nothing deforms the surface for weeks beforehand. A confined volume of superheated water flashes, and it does so inside rock that has already been chemically weakened to the point of barely holding itself up. The third candidate is an earthquake. Not necessarily a great one, just enough shaking applied to a slope that is already close to failing. Now bring back the season. Slope failures in the Pacific Northwest are overwhelmingly winter events, driven by weeks of heavy rain saturating the ground. Summers in this region are dry. The electron mudflow happened in the late summer, which removes the single, most ordinary explanation for a large landslide anywhere in western Washington. A rainstorm did not do this. What the researchers propose instead is snow and ice melt. Late summer melt on the upper mountain saturating the altered rock in the Sunset Amphitheater, raising pore pressure inside material that is already clay and reducing the amount of force needed to make it let go. That mechanism does not require magma, an earthquake, or a storm. It requires a warm summer and a mountain that is already rotten. The team has said their next step is to go through temperature and precipitation records for the period around 1507, looking for conditions that might have predisposed the region to a failure of this size. That work is not finished, and it is important to be careful here. Nobody has attributed the electron mudflow to climate, and the researchers have not made that claim. What they have done is identify meltwater saturation as a plausible pathway. If that pathway is the right one, then anything that increases summer melt on the upper mountain is acting directly on the condition that governs failure. If the electron mudflow shows what this mechanism does at the scale of a single valley, there is an older event that shows what it does when a much larger piece of the mountain goes. Roughly 5,600 years ago, the summit and northeast flank of Mount Rainier collapsed. The volume was somewhere between 3.8 and 4 cubic kilometers. Call it 40 times the threshold that the modeling treats as a sizable collapse. It began as a water-saturated avalanche of already weakened altered rock, and it transformed into a lahar as it moved. That event is called the Osceola Mudflow, and its numbers are hard to hold in your head. It filled the White River Valley to between 80 and 150 meters. It spread across 210 square kilometers of the Puget Sound lowland. It ran 70 to 100 kilometers from the mountain, which put it on the ground now occupied by the city of Tacoma and by Kent, a suburb of Seattle. When it reached Puget Sound, it did not stop at the shoreline. It continued underwater for as much as 20 kilometers. It also removed the top of the mountain. Osceola left a horseshoe-shaped crater open to the northeast, the same shape Mount St. Helens left in 1980. Rainier then spent the following millennia rebuilding a summit cone inside that scar. The peak, visible from Seattle today, is younger than the collapse, a new cone standing on the failure surface of the last one. Osceola did one more thing, and it explains why the hazard sits where it does now. That collapse stripped the intensely altered rock out of the summit, the east flank, and the interior of the volcano. It removed the weak material from those sectors by carrying it into Puget Sound. What remained, and what has continued to alter in the 5,600 years since, is concentrated on the upper west flank, in the Sunset Amphitheater region. The mountain's most dangerous face today is not the face it presented before Osceola. The hazard migrated, and the modeling and the field mapping both point at the same sector. There is a precedent on that side, too. Between 2,500 and 2,600 years ago, the Round Pass mudflow began as a sector collapse of altered rock from the Sunset Amphitheater and the Tahoma Glacier headwall. The exact source region identified as today's only qualifying collapse site has already produced one, and the ice on that mountain guarantees that whatever comes off it will travel. Mount Rainier holds roughly 156.2 billion cubic feet of snow and ice. Mount Hood, the Three Sisters, and Mount Shasta hold about 22.6 billion between them. Rainier carries close to 7 times the ice of the other major Cascade volcanoes combined, which means any collapse there has a water supply nowhere else in the arc can match. So what stands between that mechanism and the valley? A detection network and a stopwatch. Lahar monitoring at Mount Rainier began in 1995. The first version of the detection system went into the Carbon and Puyallup river valleys in 1998, and it has been expanded steadily since. 5 new stations in 2020, 14 new sites installed between 2017 and the spring of 2021, with up to 20 more planned after that. It is run by the Pierce County Department of Emergency Management with technical support from the United States Geological Survey, and it consists of seismometers and other instruments placed on the volcano's slopes and along the flow paths themselves. Understand precisely what that system does, because it is often described wrong. It does not forecast. It cannot tell anyone a lahar is coming. It detects a lahar that has already started moving, and it converts that detection into sirens and alerts. The entire value of the system is the interval between the moment the flow trips a sensor and the moment it arrives. The Geological Survey's D-claw modeling, which simulates hypothetical landslides originating high on the western flank and running down the Puyallup and Nisqually valleys, puts that interval at as little as 50 minutes for Orting. Cascades Volcano Observatory scientists give the same figure less precisely, less than an hour. Approximately 90,000 people live in the path of a large lahar from this mountain, the highest debris flow exposed population of any volcano in the United States. The Puyallup River Valley carries the greatest risk. They practice. Communities and school districts in the East, Pierce Interlocal Coalition, run lahar evacuation exercises every 2 years, and Orting runs one annually. The most recent full-scale regional exercise was held on the 23rd of April this year, with students from Puyallup, Sumner, Bonnie Lake, Orting, Buckley, Carbonado, and Wilkson walking the marked routes to high ground. It is the largest lahar evacuation drill in the world, and it exists because the road network in that valley would not clear in 50 minutes. Here is where the mountain stands right now, and what would actually change the picture. The alert level is green, and there's no reason for it to be anything else. In July of last year, Mount Rainier produced the largest earthquake swarm ever recorded at the volcano, more than 1,350 located events, thousands more too small to locate, peaking at 26 recorded earthquakes an hour. The largest was a magnitude 2.4 on the 11th of July, averaging about 4.5 kilometers beneath the summit. Nobody felt them. The Geological Survey's reading was that the swarm remained consistent with the circulation of fluids along pre-existing faults beneath the volcano, which is background activity at this mountain, and the alert level never moved. That reading is correct. It is also worth noticing what those words describe. Circulation of fluids along pre-existing faults is the hydrothermal system, the same system that has spent thousands of years converting the inside of that mountain into clay. The largest swarm ever recorded there was not a warning of eruption. It was the sound of the machinery that does the damage, running normally. 519 years have passed since the electron mudflow. The recurrence interval for a lahar of that class is roughly 500 to 1,000 years. Do not read that as overdue. An average calculated across 6,000 years of deposits does not schedule anything, and 519 years sits inside that window rather than past it. What would genuinely change the assessment is any of 3 things. Deformation monitoring on the Sunset Amphitheater headwall showing that face moving. A field result that finally identifies the 1507 trigger, a cryptotephra layer, a matching earthquake horizon, a hydrothermal explosion deposit of the right age, because knowing which mechanism did it tells the monitoring community which precursor to look for, or the completion of the detection network's build-out into the west side drainages specifically, which determines how much of that 50 minutes is actually usable. Until then, the honest summary is this. Mount Rainier does not need to erupt to kill people. It has already proven that once, and the process that will eventually produce the next one is running today, with no instrument capable of telling anyone how far along it is.